I want to share with you this problem from the AMO, the Australian Maths Olympiad, which I thought was very interesting, and it might not have been very difficult, but I thought the answer was very interesting and illustrative of a lot of things. Okay, so the problem itself is, it's a geometry question. Okay, so you have ABC as a triangle, and then you have a circle, sort of like this, and it intersects side BC at U and V, and it intersects sides CA at W and X. It intersects side AB at Y and Z. Okay. Okay, and it lies in that order. So it's U, V, W, X, Y, Z. And you're allowed to assume that AY equals BZ. And BU equals CV. BU equals CV. And you want to prove that CW equals AX. So you want to prove that this way, this X is equal to this Y. Okay. And so I guess so there's lots of ways to approach this question, but maybe I'll go through a way it's not so, it's maybe the least geometric kind of thing. I mean, one of the things that you know when you have a circle is that if you have a point here, okay, it's equal. There's an equal intercepts theorem for this situation. Okay, and you can prove it quite easily if you knew the proof, if you've seen the proof before, and if you hadn't, and you knew the proof wasn't long, then you could find it quite easily. And it's, you know, you could just use similar, like you might not be comfortable with me brushing over it. You might want to look it up, but let me state the result. So it's AY times AZ equals Y, little y, so AX times AW. Y times AW. Okay. Yeah, and you can look this kind of thing up, but really, like, it follows from this small triangle at the top being similar to this big triangle, and the angles are equal because of the cyclic quadrilateral. And then you just find the appropriate ratios. Okay. So we can start with something like that. And it's true for all three of the corners, right? So then you get, so that was at A, okay? At B, it's BZ times BY equals BU times BV, right? And at C, it's CV times CU equals X times CX. Okay. So somehow this little x is meant to equal little y in the end. Okay, so now we have to use some of these assumptions. CV and UB are equal. So maybe we can go, if CV and UB are equal, so we can go from this to the top if you want. So if CV and UB are equal, okay, then we can replace CU by BV, okay? And we can replace CV by BU. Okay, and the CX I guess, I mean, we can leave it like that for now, XCX. Okay. Now we already see that BU times BV is equal to BZ times BY, right? So this is now BZ times BY is equal to XCX. Okay, because BU times BV equals BZ times BY. Now BZ times BY, and now these are equal, right? So then BZ is equal to AY. This is AY. Okay. BY is equal to this plus this, which is equal to AZ. Okay. And so that's equal to CX plus X. AYBZ. Sorry, AYZ. And then so therefore XCX is equal to YCY. Okay? But CY is just sorry, not CY, sorry, YAW. Okay. So AW is just Y plus WX, right? We're going to call this the delta D. And CX is just X plus D. So this is X times X plus D equals Y outside of Y plus D. So this is like sort of the algebraic way of doing this problem, okay? So slow and steady but very, very sure. Each step is very easy. And then it's X squared plus XD plus YT, right? And then if you factorize it, you can get, so X squared minus Y squared, and X minus Y times D is a common factor of X minus Y times X plus Y, and then there's a D. Okay, and since this is always positive, then this is equal to 0. Okay, if two things multiply to 0, one of them has to be 0, so it has to be this one, so X equals Y. Okay. And if you never thought about it, this problem would just be kind of not that interesting and would be finished. Okay. But I reckon it's actually kind of interesting because one of the things, especially since we just did recently this course on the power of a point, okay? So the power of a point is sort of this idea that, so see, just because of where A is, it doesn't actually matter where it intercepts the circle, these lines. The product of this and the whole thing is always the same, right? That's what we said with that, okay? So that's called like sort of the power of a point. So the power of the point is that constant value that it's always equal to this, okay? And if you learn a little bit more about power of a point, you'll know that things with equal powers of a point, okay, lie on a circle, okay? And they lie on a circle that's centered with the same center as the original circle, okay? So that's kind of interesting because it kind of gives you another perspective on the problem. Okay. So now it's trying to say so now it might have something to do with the circle. Okay. And if you look at it, so let me just erase this. But we actually already know that any 3 points lie on a circle, right? That's the whole idea of a circumcircle. So any 3 points lie on a unique circle. So this triangle already lies on a circle, okay? But the thing is, this circle, the center of the circle might not necessarily be the same as the center of this circle, and we might not even try to see that it is, unless we had that power of a point viewpoint. Okay. And it actually is, because how do you work out the center of a circle? Well, anytime you have a chord, right? So you have the smaller circle, the center will always lie on the perpendicular bisector of that chord. Okay? But if you look at the bigger circle, okay, the perpendicular bisector of the chord of the bigger circle is actually still on this line, because we assume that these other parts are equal as well. So these two parts are equal already, and if these two parts are equal, then this is the bisector of the bigger chord. Okay, and the same reasoning on this side says that the centers, being the intersections of these perpendicular bisectors, are actually the same point. Okay? So that's already enough to sort of conclude that these powers of a point are equal, and then sort of do algebra to get that x is equal to y, like we did before. But the nice thing is that we can actually continue in this theme and not have to do that. Okay? So you can actually continue this theme and say, well, the point is the center is in the perpendicular bisector of this, right? But we already located the center. Okay? So therefore, the perpendicular bisector of the smaller chord, okay, must actually be equal to the perpendicular bisector of the bigger chord. Okay, and from that it follows directly that x equals y. Okay. And I guess it's kind of a funny proof, because that whole time you have this idea of a power of a point in your mind, okay, but nowhere does it actually manifest itself explicitly in the proof. Okay. But in a sense it motivated the whole thing. Okay. And I'm sure if you were more geometrically inclined, you might be able to come up with this kind of thing from just first principles, maybe. But I still find it very interesting how you can come up with a very elegant solution to this problem, okay, while thinking entirely about a concept such as the power of a point, and not really have that concept like explicitly appear in the proof. Okay, so the power of a point, you know, this length times this length, we never really actually use it explicitly if we draw the extra circle. Okay, but it's something, somehow it was crucial for us to think of it. But I found that problem very interesting, and I hope you do as well. So that was the AMO 2016 question 2.